So we've seen the basics of the response design where we saw that stationary point right at the very last using those canonical variates that we extract from the model. But let's go back and look at an application here. Okay, so this is a cake baking example. The mix recommends 35 minutes at 350, but there may be an optimum time and temperature that makes a better tasting cake. So we can begin with a first order design in which the baking time and the temperature use a 2 to the second factorial with 3 center points. So it's important, and I think it comes up in the notes in a bit, that you center the points so that you're really just measuring the change from the mean. So it may make sense to have these points centered at those recommended values of 35 minutes and 350. But you typically just use the numerical mean at whatever you set for your different levels. Okay, so we're going to use, in order to have the centered points, we're going to assign -1 to 33, 0 to 35, and 1 to 37. So we are using, what I would generally suggest here. Similarly, -1 is for 350, -1 for 340, 0 for 350, and then +1 for 360. So those are our design points at each time and temperature combination. So the response is the average score that is assigned. I guess they did some taste testing. That's called a palatability score, with the higher values being more desirable. Okay, so we can see at our design points, -1, -1, the palatability score is quite low. We see a potential high point at 0, 0. All right. We see our 3 replications for the central time points, and then our different deviations from those central time points. All right, so that begins that first example. Let's continue and look at how that cake baking example data would be analyzed. So we had that 2 to the second design with 3 center points. Those would be considered the stationary points for our design. The first order model is going to have that constant, that f of x naught, and then those terms that describe that departure from that base value. With 7 design points, there's going to be 4 degrees of freedom for the error, and the only replication in the design is at those 3 center points. You see this a lot. It's not optimum, but it often occurs just due to lack of time and resources. So because of that, we're going to have 2 degrees of freedom for the pure error. That's not ideal, but that's what we have. So let's take a look at some of the output for this. This is out of Minitab here. We have the coefficients for our temperature and time variables, and we see our grand mean also estimated. There's a ANOVA breakdown of the model. We see the pure error with the 2 degrees of freedom, the lack of fit test for higher order forms, or lower for testing the higher order form of the model, and then the overall residual error 4, which is broken down into the 2 and 2. Our total degrees of freedom is, of course, 6 for the entire model. We do see that there is a lack of fit. We know that from this line, meaning we probably could improve the model, and that the direction of the steepest descent here is not going to be a good descriptor. So we might need to move on to a second order model. So let's go back to the notes a little. Okay, we saw that first example for the cake baking experiment, and so I want to go back and see kind of how it gets laid out in the textbook for testing. You could see that we assessed in that cake baking example the fit of the model. we estimated that error and then estimated the lack of fit. So remember, we had the 4 degrees of freedom for the whole error, for the total error. Our pure error was 2 degrees of freedom, and the remainder was lack of fit. And remember, we ended with an assessment that the first order model had significant lack of fit. So that steepest ascent is probably not a good descriptor of the actual effect of the time and temperature change on the palatability of the cake. Okay, so I went over this in the example, so I'm going to skip it here. But this is generally how we use that central composite design that we saw. I felt like this was way too abstract and didn't want to show you this without seeing kind of a simple example of it. We'll go to that table 19.1 too in a minute. But you begin with your 2 to the q factorial. We had a 2 to the second for the cake baking example. The corners are going to be at +1 and -1, and the resolution level 5 fraction can be used as an alternative in some cases. Center points are at 0. So remember, our center points were at where we had the 3 replications at 350 and a time of, I think it was 35 minutes. And then you can add in axial points. We did not see that in our example. Okay, in general, once you've assessed your first order model, and it indicates there's a lack of fit, you may want to find where there might be some degree of curvature, and that entails a second order design. Okay, so if there is a lack of fit for the first order design, like we saw in the cake baking example, then you want to augment your first order design to a second order design. So that's where we are with our cake baking example. And so this is going to be our next step. If we had seen no lack of fit, however, we would have moved off in our direction of the steepest descent. If bigger is better, with the palatability ratings, that was the case, but you want to make sure that that's the case. You don't want to just blindly do that. And as long as you keep ascending, you know that you're getting bigger, which is presumably better. Once you get to the top, you put down another first order design, and you return to your step 1 and redo. But we're here at step 1. We've determined that there is a lack of fit. Let's go back to the example in the text. Okay. You can see this is a lot of the material. This is a little bit more detail about that beta matrix and then how you derive that H matrix that gives you your canonical covariates. If you need help on that, just let me know, but I wouldn't worry too much. You can see it's just a decomposition of the matrix. That's all that it really is. And so it just creates a projection from that matrix. There we go. Back to the cake baking example. So the first order model in that cake baking was not adequate fit. In particular, Gary points out the contrast between those factorial points and the central points, or center points, indicated that there's some sort of curvature in the response. So that's when you know you need a second order model, because that model's a curved surface rather than a flat surface with just the levels in the surface. So we have those factorial points and then the 3 replications of those center points in our example. Looking in table 19.1, let me go to that. Okay, to give us an understanding of how we need to modify the cake baking example to get a better response surface model, I'm just going to introduce to you that the most common way to do this is using a central composite design. Without going into all the theory behind this, CCD is basically just a set of factorial points like we just went over. Axial points, which we'll talk about more in a second, and then the center points. We've already defined our factorial points and our center points. We just need to go over the idea of the axial points here. So the factorial points are those points from the design that are coded as the plus or minus 1. And we're going to go with resolution 5 or greater on these. The axial points have one design variable at plus or minus some alpha, and this is a design that value that comes from a theoretical model, I guess is the best way to say that. So going to take a look, we can choose our points for alpha and then the number of those center points m. Remember, for our cake baking example, we have m equal 3. And so here, if we run our CCD using incomplete blocks, where the first block has the factorial points and then the center points, then the second block will have the axial points and the center points. So for example, so you can see here our center points are 3. This, from the theoretical model, we get our axial points is 1.414, and the number of blocks in the factorial is 1. Okay, the center points per factorial block is again 3. Okay, so we're going to make use of this design. I'm kind of skipping through a lot of detail here just so we can move on. But take a look that we have the 2 blocks as defined by that CCD design, and our axial points here in block 2 are defined by those axial values here. Okay, and we still have our number of repeated center points as 3 within each block. So you can see that we have expanded this design so that now we have, take a look, we've got 7 within each block, so there's 14 observations now. So if we design our model this way and we analyze those results using that CCD or central composite design that comes again from a theoretical model, we can see now that our lack of fit is no longer significant, meaning we have a better form of a model that's fitting the curvature of the plane well. And in fact, we have an interaction term that is significant within our model. Notice how well we can model these interactions, or that interaction, I should say, between the time and temperature. Okay, so let me get back up here. I was mentioning that interaction term. I had to stop the video for a second. Notice that the model indicates a very good fit, actually. I kind of wonder about how good of a fit this really is. Let's talk a little bit more in class about how much confidence we should have in a model like this. But in general, I think a second order model is a reasonable approximation here and an improvement in fit over that first order model. We need to think about that canonical analysis for the surface. So let's look at listing 19.3. Here we have the different components that will help us understand those values. So I don't know, for me, I think it's most informative to look at the lambdas. So remember, when the lambdas are both negative, we are describing a maximum point. So we can find a maximum at a particular point where the response has a value of 8.347, and values for the stationary point is 0.4 and 0.2. So we'd have to rescale that, but that would be a little bit higher than the recommended temperature of 350 and a little bit longer